Welcome to my talk about perforated profiles. I am Anna Parlisson. I am a consultant engineer and I offer consultancy to develop steel cold form sections and structures as well as composite slabs in accordance with the Eurocodes. I am presenting here the calculation method as developed within the GRISP project for profiles with perforations arranged in squares. After a brief introduction to the topic, I am going to present the state of the art before the GRISP project in order to help you understand why the present methodology was developed. I am also going to describe the extensive test program which was performed in order to provide the required data as well as the results of the testing analysis. Then, I am going to explain the methodology to calculate the effective section and the moment resistances of a profile with perforations arranged in squares. This methodology is proposed as an amendment on Eurocode 313. Lastly, I am going to introduce the Excel files which were implemented to calculate span moment resistance and support reaction and moment reaction interaction and internal support for a profile with perforations arranged in squares in the web and a profile with perforations arranged in squares in the flange. Let me introduce the topic of the talk. In this picture we can see a steel profile which is commonly used for structural roof decking. The picture on the left shows a profile with perforations in the webs. The picture on the middle shows a profile with perforations in the flanges. And the picture on the right shows a profile with perforations in the webs and in the flanges, which we'll call total perforations. For architectural reasons and to increase acoustic performances, the perforated profiles are increasingly developed and used. There are different types, geometries, and distributions of perforations. The picture on the left shows perforations arranged in triangles, whereas the picture on the right shows perforations arranged in squares. The design rules for perforated profiles are given by the current Eurocode 313, but these design rules are only given for perforations arranged in triangles. Here we have the section of the Eurocode which deals with the profiles with perforations arranged in triangles. It stipulates that these specific sheetings may be designed by calculation, provided that the rules for non-perforated sheeting are modified by introducing an effective thickness. TAF for gross section, TBF for effective section, and TCF for the resistance of a single web to local transverse forces. The effective thicknesses are a function of D, the diameter of the perforations, and A, the spacing between centers of the perforations. Thus, at the beginning of the GRISP project, we could observe that despite the frequent use of perforations arranged in squares, there was no information given by the Eurocode or by the literature on how to take such perforations into account when designing steel profiles. Actually, the only way to design such products is to carry out tests according to Eurocode 313. But such tests are expensive and time-consuming. So we could confirm that there was a real lack of data and relevant knowledge on how to determine the resistance of steel profiles with perforations arranged in squares, and that an innovative methodology was necessary. This state-of-the-art has allowed us to determine the objectives of the GRISP project and the methodology to be applied to achieve them. The main goals were to determine the missing data through a huge testing program and developing and validating a calculation method thanks to the test analysis. This method was proposed as an amendment on Eurocode 313. Now, let's have a look at the extensive testing program performed within the GRISP project. The first aim was to determine the influence of perforations arranged in squares on local behavior. The second aim was to determine the resistance values of tested profiles that we can see on the pictures. The tests were performed on profiles without perforations and on profiles with flange, web, or total perforations arranged in squares. The third aim was to compare the values obtained for profiles without perforations with values for those with flange, web, or total perforations arranged in squares. The fourth aim was to assess the impact of these perforations on the resistance of the profile. The final aim was to define a calculation method for profiles with such perforations. Here is a view of the local testing samples. Flexion and tensile testings were performed on samples without perforations, on samples with perforations arranged in squares, and on samples with perforations arranged in triangles. Now look at the local testing results. The analysis of the local tests led to an effective thickness for sheeting with perforations arranged in square as a function of thickness for sheeting with perforations arranged in triangles. TF square is equal to ρ multiplied by TF triangle, where the ratio ρ is equal to 0.93. A geometrical relation was determined between A and E for the same surface and the same percentage of perforations, where R is the spacing between the centers of perforations arranged in triangles and E is the spacing between the centers of perforations arranged in squares. Concerning the global testing, single span test, end support test, and internal support test were performed according to Eurocode 313 Annex A. Here we can see the pictures taken during the single span testing. On the left, we have a profile without perforations, then a profile with flange perforations, followed by a profile with web perforations, and on the right, a profile with total perforations. The observed failure mode for all the profiles was the buckling of the upper flanges near the midspan. The moment resistance was determined. Here we have the end support testing pictures. On the left, you can see a profile without perforations, then a profile with flange perforations, followed a profile with web perforations, and on the right, a profile with total perforations. The observed failure mode for all these profiles was web crippling. The resistance at end support was determined. Here are the pictures taken during the intermediate support testing. On the first one, we have a profile without perforations, then a profile with flange perforations. On the third, a profile with web perforations, and finally a profile with total perforations. The observed failure mode for all the profiles was a crippling and buckling of the web. The resistance to the combined moment and support reaction was determined. We can see on this table the decrease of the resistance induced by web perforations, flange perforations, and total perforations. The results obtained for profiles without perforations and for profiles with perforations arranged in squares allowed us to make comparisons and to assess their impact on structural behavior. The major results were that web perforations and flange perforations induced the same decrease of the moment resistance, whereas web perforations induced a much bigger decrease of the reaction resistance than flange perforations. Of course, total perforations induced the most important decrease of the whole range of resistances. The next step in our scientific process was to come up with a calculation method for moment resistance, web crippling resistance, and moment reaction interaction. For profiles without perforations, resistances were calculated according to Eurocode 313. For profiles with perforations arranged in squares, resistances were calculated with Eurocode 313 formulas for perforations arranged in triangles, but by replacing TF by 0.93 multiplied by TF and A by 1.07 multiplied by E. Eventually, the resistances determined by calculation, as defined previously, were compared to the resistances defined by testing. For perforations in the web and in the flange, the difference observed between the calculated moment resistance and the tested one was current with the difference observed for the profiles without perforations. This comparison confirmed that by replacing TF by 0.93 multiplied by TF and A by 1.07 multiplied by E gives safe and current results with the testing results. In the case of web crippling resistance, it was quite different, because for the profiles without perforations, the calculated moment resistance was much lower than the tested one. It confirmed the observation highlighted in the literature, showing that the web crippling formula gives results which are very different and underestimated compared to the testing results. Thus, consistent with the 10.4 clause of the Eurocode 313, only A is replaced by 1.07 multiplied by E. These results have allowed us to submit an amendment proposal on Eurocode 313, consisting in replacing the 10.4 clause by another one dealing with perforations arranged in the shape of equilateral triangles and in the shape of squares. The amendment specifies that both sheeting with perforations arranged in triangles and perforations arranged in squares may be designed by calculation on condition that the rules for non-perforated sheeting are modified by introducing the respective effective thicknesses. For gross section and for effective section, the formulas for triangular pattern are the current formulas from Eurocode 313, whereas the formulas for square pattern are adapted. A is replaced by 1.07 multiplied by E in TAF and in TBF, and TBF is multiplied by 0.93. For the resistance of a single web to local transverse forces, the formula for triangular pattern is the current formula from Eurocode 313, whereas in the formula for square pattern, A is replaced by 1.07 multiplied by E. For the final part of my presentation, I would like to introduce Excel files which were implemented in order to calculate the resistances for profiles with perforations arranged in squares. These files were validated by comparing the results with the results of the testing. Moreover, these calculation methods have been made available to a number of industry users to check their relevance with the purpose. Thanks to these tools, you will be able to calculate span moment resistance, web crippling resistance, and moment reaction interaction at internal support for profiles with flange perforations arranged in squares, with a web stiffener and a flange stiffener. You will also be able to calculate span moment resistance, web crippling resistance, and moment reaction interaction at internal support for profiles with web perforations arranged in squares, with a web stiffener and a flange stiffener. To conclude, it is important to underline the following points. Firstly, this design by calculation method was supported, checked and validated by a huge testing program performed within the GRISP project. Secondly, 4 Excel files were implemented in order to calculate the resistances of a profile with perforations arranged in squares. Lastly, this method was proposed as an amendment on Eurocode 313. I hope I have contributed to making you more familiar with this methodology. I invite you to follow my 3 other talks related to hold profiles, steel decks with embossments, and steel decks with outward stiffeners. I thank you for your attention.